So now we're gonna talk about the periodic table of elements. That's the next part. And the periodic table looks something like this with the 1, 2, row 1 and 2 with the S block. And then from 2 to 12 is gonna be, oh shit, there's no back button. 2 to 12, 3 to 12, it's gonna be D block. And from 13 to 18, P block. With an exception of the first element in the P block being S block, but it's 13 to 18. Oh, there's one more. At the second last and last two parts of the D block is extended to form the F block. It's from 3 to 17. I'm a bit confused, but that's F block. So now let's talk about, let's make it two columns, and this side represent from left to the right of a periodic table, and this side represents top to bottom. And the first trend would be for atomic radius. Atomic radius decreases from left to right as when we go from left to right, the atomic number increases, but not the shell number or number of shells. So there's going to be more protons on the same atom the more right we go. There's therefore more electron pull. Like the nucleus is going to pull the outermost electron, resulting in smaller atomic radius. And the opposite is going to be for top to bottom, where we do have increasing atomic number resulting in more protons, but another thing is we have more, how do you say, energy levels, so there's going to be shielding effect. So yeah, that's why from top to bottom atomic radius usually decreases, and this is just a standard form. There are exceptions. The modern periodic table is still not the best. It's the best we have, but it's not perfect. Now what atomic radius, electron affinity, ionization energy. Ionization energy, it's the energy required to eject an electron from the outermost shell. And that would be first order ionization energy. The more electrons we eject, that will be second order, third order. It just goes further. So ionization energy, that is gonna, from left to right, ionization energy is gonna increase due to smaller atoms, uh, small at smaller radius, smaller radius, more energy required to eject. Now for from top to bottom, that's the opposite case, because ionization energy decreases, less energy is required due to less nuclear pull, or less pull from the nucleus. That's what. So bigger the atom, bigger the atom, less IE. Now what's the next concept would be electron affinity. Energy required, that's the energy required to add an electron into the atom. So that's going to show the opposite reaction compared to ionization energy. For example, electron affinity is lower for smaller atoms because less energy required to add atom, because high nuclear pull due to small size. Smaller atoms have higher nuclear pull from the center, or from the protons, so it's easier to add an electron, if you know what I mean. But in the case of bigger electrons, electron affinity increases. More energy required to add electron due to less interaction from the nucleus as the atomic radius is big. The shielding effect, all these are what contributes to the higher electron affinity. Now, what was it? Electron affinity. What's next? Electronegativity. Electronegativity, that's the tendency, you could say, tendency of the atom to pull in an electron. It's similar to electron affinity, but yeah, just like that, electronegativity, let's write En, is lower for smaller atoms as more protons pull more electrons, or has the tendency to pull more electrons, while in the case of larger atoms or larger radiused atoms, electronegativity increases. Sorry. Electronegativity increases for smaller atoms as it wants to pull in, and electronegativity is lower for bigger atoms. Large size results in less tendency to pull. Forgive my vocabulary, I'm still learning, okay? Less tendency to pull in external electrons. Now I'm gonna be writing the last one, or almost the last. It's called effective nuclear charge. It's a Z effective. That's what the symbol is for. Symbol is usually referred as Z effective. What was Z effective? Effective nuclear charge. That's the let me just cross check, okay? Yep. So effective nuclear charge is you could say it's almost similar. It's the interaction between the nucleus and the valence electron. Valence electron, outermost most electron. So Z effective is higher for smaller atoms, as due to their smaller size, the nucleus has more effect on the external electrons. Due to small size, the nucleus attracts the outermost electron. Now, effective nuclear charge for bigger atoms is going to be low because due to the large radius, shielding effect, etc. Less attraction between the nucleus and the outermost shell. No, that's not correct. Outermost shell. Now that would be, these are just common trends. There are still a lot of exceptions for these, especially when it comes to electron affinity and F block. Lot of exceptions with F block. So there's a lot of exceptions, but this is most of the trends that are seen in the periodic table. Effective nuclear charge, electronegativity, electron affinity, ionization energy, atomic radius. And yeah, this is basically what the periodic table looks like. And I don't know if I did not mention, but the S block, D block, P block, F block, these for percent, the valence electrons shell. Yeah, this represents where the valence electrons are situated. Especially for these two, it's going to be S block, T block, P block. That means 2 electrons, 6 electrons, 10 electrons, 14 fucking electrons. Hell yeah. Well, I think that's basically it for periodic table. Peace!